Welcome to The Industrial Edge, the podcast where innovation meets precision. I'm Jen Meza.
And I'm Brad Jens.
Today we're embarking on a deep dive into something we're calling industrial motherboards, the hidden heroes revolutionizing modern industries.
That's right.
You know, we hear so much buzz about AI, machine learning, all this groundbreaking software, but what about the actual foundational hardware, the stuff silently powering these breakthroughs, especially in the really demanding, unforgiving environments?
It's exactly what we want to unpack today. Our mission here is to explore the absolutely critical, maybe often overlooked role of industrial motherboards.
Okay.
We'll get into why they aren't just, components, but really indispensable strategic assets, how they enable cutting-edge tech like AI at the edge,
Right.
and crucially, why understanding their capabilities gives you a significant competitive advantage. Think of this as your inside look at the invisible backbone of modern industrial operations.
Okay, let's dive in then. When you think about, say, the incredible precision of a robotic arm-performing surgery, or maybe the relentless, intricate systems keeping a massive soda production line perfectly synchronized, have you ever really stopped to think what's inside? It's not just those flashy AI algorithms doing all the heavy lifting, is it?
No, not at all. It's something far more fundamental and, like you said, far more robust.
So what are we talking about here?
We're talking about, engineered warriors, essentially, working silently, tirelessly, reliably in the background. These are industrial motherboards.
Okay.
And they are profoundly different from the consumer PC motherboards you'd find in, say, your laptop or desktop at home.
Yeah, I can imagine.
Think about the conditions your average computer works in. Probably a climate-controlled office, right? Maybe a home desk.
Sure, pretty stable.
Now, imagine putting that same board onto a factory floor or inside specialized medical equipment in a busy hospital.
My laptop would probably give up the ghost after about 5 minutes. The comparison just breaks down instantly, doesn't it?
It really does.
Your typical consumer motherboard wouldn't last a day, I bet. These industrial ones, they're built to withstand, frankly, incredible, often extreme conditions. Stuff that would just obliterate standard electronics.
Absolutely. The engineering involved is, it's really on another level. Let's take temperature extremes.
Okay.
We're talking about reliable operation from a frigid minus 40 degrees Celsius
Wow.
all the way up to a scorching plus 85 degrees Celsius.
That's intense.
Your standard laptop would either literally freeze up, components shutting down, or, melt, solder joints failing under that heat stress.
Right.
Industrial boards, though, they use specialized components rated for these wide ranges. Often they have passive cooling designs, too, to handle heat without relying on fans that can fail.
And it's not just temperature, right? Factories are notoriously rough places for equipment.
That's right, constant vibration. Think about manufacturing plants, mobile applications. That continuous shaking would quickly rattle standard components apart. So industrial boards are often designed with reinforced PCBs, locking connectors, really robust mounting systems to handle that continuous shock and vibration.
Okay.
Then there's chemical exposure. Right. That's critical in medical settings or food processing, maybe, where you have sterile cleaning agents or even corrosive industrial chemicals around.
How do they handle that?
Often with something called conformal coatings. It's basically a protective layer, seals the electronics from moisture, dust, corrosive elements.
So it's not just about making existing tech tougher, it's really re-engineering it from the ground up.
Exactly.
And beyond just surviving, these boards are often expected to run 247 for years without a single break.
That's a huge point. We're talking maybe 10, even 15 years of continuous, reliable performance. That's an eternity in the consumer tech world.
It really is.
And don't forget, electromagnetic interference, EMI. Those invisible energy waves that can scramble a standard computer's brain.
Right, near heavy machinery or something.
Precisely. Industrial boards often integrate specialized grounding, multi-layer circuit designs, shielding. It makes them virtually immune. They operate flawlessly, where consumer tech would just freeze up or crash.
The real insight here, then, isn't just that this hardware is tougher, it's that the whole engineering philosophy behind it prioritizes predictable longevity over, rapid obsolescence.
Yes. Reliability becomes a strategic asset in itself.
It's like comparing, a family car to a military tank.
That's a good analogy. Both have engines, right? But you wouldn't take your sedan into a combat zone. These boards are built for that industrial combat zone and built to last for decades.
And this leads us perfectly into our next point, because this whole AI revolution, it isn't just changing software, is it? It's completely reshaping the demands on the hardware underneath.
Absolutely. The incredible capabilities of AI, they need an equally robust foundation. And often that foundation needs to be geographically distributed.
Which brings us to edge computing.
Exactly. That's where we're seeing a huge and accelerating shift. Think about let's call it the old way.
Okay.
You collect tons of data from sensors, maybe on a factory floor, then you package it up, send it all the way to a distant cloud server, you wait for it to be processed, and eventually you get the results back.
Which works fine for some things, but
for critical industrial uses, those milliseconds of delay, those potential network hiccups, they're just unacceptable. Lives could be at stake, or millions in production losses.
So if that old way creates bottlenecks, how does edge computing fix it? How does it re-architect the process?
It flips the model. The smart way isn't just about speed, though that's part of it. It's about distributed intelligence. Meaning processing the data instantly, right there at the sensor or the machine where it's actually created. Making decisions in real time, in milliseconds.
Okay, give me a real-world example, maybe here in the US.
Sure. Think about a manufacturing robot in, say, an automotive plant right here. With edge computing, it can spot a tiny micro defect on an assembly line component and adjust its own behavior instantly. No round trip to the cloud, preventing potentially thousands of dollars in waste or recalls right then and there.
Wow, okay, that's immediate impact.
Or picture medical equipment, maybe in a rural clinic that doesn't have super fast internet. It can analyze critical patient data in real time right at the bedside.
Without relying on that internet connection.
Exactly, in situations where seconds can literally mean the difference between life and death.
So the key insight is?
The key insight is that this whole edge computing revolution, with its intense AI workloads and the absolute need for real-time decisions, it's only truly possible because of these specialized industrial-grade motherboards.
Right.
They provide that critical reliability and the processing power exactly where it matters most, on-site, locally, not miles away in a data center.
It's fascinating how every industry seems to have its own unique, really complex challenges. And for those specific challenges, a generic off-the-shelf solution probably just won't cut it, right? You can't just plug in a standard component and expect it to meet these highly specialized, often mission-critical demands.
That's precisely why custom engineering becomes absolutely essential. It's really how these specialized motherboards are transforming entire industries.
Okay, like where?
Take healthcare, for instance. An arena where lives literally depend on reliability. Medical devices have incredibly specific needs.
Such as?
Well, strict FDA compliance, for one. That means meeting stringent government standards for safety, effectiveness, quality, built right into the design from the start.
Okay.
They also need compatibility with sterile environments, think operating rooms, and life-critical reliability standards that go way beyond anything a consumer product would ever face.
Makes sense.
Plus, these boards need seamless integration with highly specialized medical sensors, imaging equipment, instruments.
So the custom engineering isn't just about meeting specs.
No, it's more than that. It's about shifting from being reactive, fixing generic boards when they fail, to being proactive, designing the hardware to anticipate and prevent the specific problems, exist in that operational environment.
So reliability becomes a direct competitive advantage.
Absolutely. It dramatically impacts the effectiveness and the safety of those medical devices.
And it's not just healthcare, right? Thinking about a major U.S. manufacturing facility, that zero downtime challenge must be huge.
Oh, absolutely huge. A production line halting, even for just a few minutes.
Yeah.
That can translate to millions in lost revenue, wasted materials.
You're right.
So in manufacturing, the critical need is for components that ensure continuous operation. Minimal interruption, that's paramount.
And custom boards address that directly.
Yes, every custom engineered motherboard is designed with that specific goal in mind. Prevent costly downtime, maintain peak efficiency. For example, a bespoke board might have redundant power inputs, so if one fails, the other takes over instantly. Or specialized watchdog timers that can automatically reboot the system if it freezes, preventing a long stoppage. Or even unique shapes and sizes, form factors, to fit perfectly into existing, maybe cramped, industrial enclosures.
So it's not just durability, it's engineering solutions for specific business vulnerabilities.
Exactly. Addressing the financial and operational weak points head on. That's what makes the difference between sustained success and, costly failure.
It's incredible to see how far these foundational technologies have already come. But what does the roadmap look like? Where are industrial motherboards heading next?
Yeah, the future is actually already taking shape. There are some really exciting trends emerging.
Oh, like what?
What's intriguing is how these trends build directly on that need for even more robust, intelligent, and interconnected hardware. I see 3 key trends really driving the next generation.
Okay, trend number 1.
First, AI gets smarter at the edge. Future boards won't just support AI calculations, they'll integrate dedicated AI accelerators.
Like specialized chips.
Exactly. Specialized processing units designed specifically to handle complex AI math much faster than a general-purpose CPU can, and optimized for specific applications.
So what does that enable?
Imagine surgical robots that can learn and adapt during an operation, reacting to unforeseen variables on the fly. Or manufacturing systems that don't just detect failures, but predict them with uncanny accuracy before they happen, all processed locally, instantly.
Wow. So it's not just number crunching, it's embedding real intelligence right into the hardware for adaptive operations.
Precisely. Okay, second trend. We're seeing an explosion where everything connects to everything. The industrial IoT, the Internet of Things, is growing exponentially.
More sensors, more devices online.
Which means motherboards have to support an incredibly diverse range of connectivity options. Everything from traditional industrial protocols, things like Modbus, Profinet, to the cutting-edge wireless standards like 5G, Wi-Fi 6E.
And why is that so important?
This connectivity is the backbone for really powerful applications.
Yeah.
Think predictive maintenance, where machines basically tell you they need service before they break down.
Preventing those costly outages.
Exactly. It also enables remote monitoring of vast facilities, think oil rigs, sprawling agricultural operations, and seamless enterprise integration, tying all these different systems together into one cohesive data network.
Okay, smarter AI at the edge, more connectivity. But with all that connection comes risk, right?
Without a doubt. And that leads directly to my third key trend. Security becomes standard, not an afterthought.
That seems critical.
It is. With increased connectivity comes increased vulnerability to cyber threats. That's why the next generation of boards will feature hardware-based security elements baked right in. Things like trusted platform modules, or TPMs.
Okay.
Secure boot processes, which prevent unauthorized software from even loading when the system starts up. And encrypted communication as standard features.
So these won't be expensive add-ons anymore.
Increasingly, no. They'll be built in from the ground up. Essential layers of protection, safeguarding critical infrastructure against constantly evolving threats.
Now, here's something crucial, I think, something consumers rarely think about, but it's absolutely vital in industry: the entire life cycle of the technology.
Oh, that's a fundamental difference.
Huge. It's not just about buying the board, is it? It's about what happens over its entire operational life, often years or decades.
This is where industrial applications completely diverge from consumer electronics, where, let's be honest, rapid obsolescence is often part of the business model.
Get you to buy the next version.
Right. Industrial applications demand a totally different approach. Long-term support is non-negotiable. The foresight required here is really fascinating.
How so?
We're talking about things like proactive component monitoring, systems and processes to know that certain parts might fail before they actually do.
So you can schedule maintenance during planned downtime, not have a crisis repair?
Exactly. Then there are advanced change notifications, getting a minimum of, say, 90 to 180 days notice if any component used on the board is going to be changed or discontinued.
So you're never caught completely off guard?
Never. That's a universe away from finding out a key chip in your phone is obsolete only when the next model comes out.
Oh, true. What else?
Suitable replacement identification. When components inevitably do become obsolete, there's a plan, and tested alternatives are identified to ensure continuity of supply and functionality.
Right.
And finally, end-of-life stocking strategies. Actually planning and holding inventory of critical parts to guarantee they remain available for years, sometimes decades, after production stops.
That level of planning is incredible.
Imagine a critical medical device, maybe FAA-certified equipment, or a key factory robot built on consumer-grade parts. If a specific chip fails after 5 years and the manufacturer says, "Sorry, we don't make that anymore,"
You're stuck. Complete system overhaul, maybe? Massive downtime, regulatory issues.
all of the above. Industrial lifecycle management prevents that kind of catastrophic ripple effect. This long-term thinking isn't just a feature, it's a defining characteristic of industrial solutions. It ensures not just initial reliability, but sustained longevity, operational stability. It's really about a long-term partnership and keeping things running.
Okay, so let's try and synthesize all of this. What's the ultimate takeaway for our listeners when we bring it all together? Industrial motherboards. They aren't just components, are they?
No, not at all. They are strategic investments, period.
They're the bedrock of competitive advantage.
That's the bottom line. These specialized solutions don't just enable operations, they actively create a distinct competitive edge.
How?
Well, whether you're developing those AI-powered medical devices we talked about, where unwavering reliability literally saves lives, or you're operating manufacturing lines, where you absolutely cannot afford a second of downtime. These boards are paramount. They are essential for deploying those edge computing solutions that deliver real-time, on-site decisions, making your operations faster, smarter, more agile.
Right.
And they're the foundation for building truly robust systems designed to operate reliably for decades, protecting your significant long-term investments. The examples we've touched on. They represent real applications, often here in the US, where this level of custom engineering and industrial-grade reliability made the concrete difference between operational success and frankly, costly disruptive failure.
So the question really isn't whether to consider these solutions.
No.
But maybe how quickly you need to integrate them.
Precisely. The real question isn't if you need specialized motherboard solutions for demanding applications, but how quickly you can implement them to stay ahead of competitors who might still be relying on generic, off-the-shelf hardware.
Because generic solutions
yield generic results by their nature. Custom-engineered, industrial-grade technology, on the other hand, delivers tangible, measurable, sustainable competitive advantages.
So a final thought for everyone listening. As you go about your day, maybe think about the hidden heroes in your own operational infrastructure. What foundational, often overlooked technologies might actually be holding you back? Or, conversely, what might unlock your next big competitive advantage if you paid closer attention?
We'll be back soon with more innovation, expert perspectives, and game-changing technologies powering the next industrial revolution. Until then, stay connected with Contec Connect.